So, okay, next speaker of this session is Pierre Vanhove. The title is Mirroring Towers of Feynman Integrals. Please.
So thank you very much for the invitation to this very nice conference. And it's pretty impressive to talk after Maxime. So, but in a sense, I mean, what I'm going to say has some relation to what Maxime said in his lecture, because I want in this presentation to show you that if you look very closely at Feynman integrals, so I'm really talking about quantum field theory, Feynman integrals, the thing that you have learned, I mean, a long time ago, certainly in the first year of university, show very, very surprising properties, and actually even the one that people use to compute top quark corrections can be expressed in terms of local Gromov-Witten invariant, and they can be computed, I mean, in a sense, evaluating the Feynman integral using mirror symmetry. So, I mean, all these things look certainly very surprising to you, but actually, this is what I want to tell, and this is based on some work that will hopefully appear soon with Chuck Doran and Andrei Novoseltsev. But this piece of work that is the topic of this presentation is actually part of a long program. I mean, a program I started a few years ago with Spencer Block to give, to understand the motive of Feynman integrals and to see Feynman integrals are period of mixed motives. So let me first start with physics motivation, because this is where my motivation comes from. And so essentially what we want to compute is we want to compute scattering amplitude. So here I'm describing just a two-body scattering, two scattering. And this computation is very important in particular for this signal. So this is the gravitational wave signal that people observe from the merging of two black holes. And actually, as we explained with my collaborators from the Niels Bohr Institute, what you can do is that you can compute a scattering amplitude, quantum scattering amplitude, and extract a post-Minkowskian expansion that is purely classical from that. So the point is that if you really want to do something useful for the community of gravitational waves, you need to go to some higher loop order, and at some point you need to be able to evaluate these integrals explicitly. And so, and as you know, I mean, computing Feynman integrals is a very, very complicated problem that particle physics and Higgs, for the Higgs physics, people have looked at a lot, or even in solid state physics. So in a sense, this is where the motivation comes from. And I want to convince you that actually there is a lot of mileage you can get by having the reformulation I'm going to tell you in terms of motives and for addressing that physical problem. So physics argument tells you that if you have a n-loop amplitude, so L is the order in perturbation. So it's only I'm only going to talk about perturbative physics. No, there is no non-perturbative physics. So physicists have been convinced themselves that actually any quantum field theory at a given order in perturbation involving n particle can be expanded as a finite sum of some integrals. So they are not a priori supposed to be Feynman integrals, but they turn actually to be some very special class of Feynman integrals times some coefficient. And whether or not you are considering QCD or gravity is just a matter of when you know the basis of integrals to tune the coefficient. So the theory you are considering is just selecting the rational coefficient that depends on the kinematics. So the thing is that as long as you know the basis of integrals, you are happy. And in this decomposition, there are rational functions because these integrals are multi-valued functions in the complex energy plane. And essentially by this construction, you look at the discontinuities And this is the way you can try to understand this basis of integrals. So the thing is that, of course, what is this basis precisely? So there are physics arguments saying that there is it's finite, so there is some upper bound, but already from two-loop order, we don't know what is the explicit basis. Okay, so I will tell you something about two-loop, and so actually, what are actually the functions there? So I said the functions are multi-valued functions in the complex energy plane, so they are very highly transcendental functions with a lot of singularities, so they are very, very complicated beasts. And how do you achieve in practice such a decomposition? So for me, I mean, a Feynman integral with L loop and n internal edges is given in a parametric way by some integrals over the positive quadrant of some differential form in projective space. So the number of, so I'm going to see if you have n internal edges, I am in Pn minus 1. And here there are the Zeeman-Zig polynomial that I will present in the next slide. And in this presentation, what's happening is that, as you can see, so the powers of there are polynomials. The power of the polynomials is n, this is an integer. This is L, the loop order, it's an integer. And this is the space-time dimension. It could be an integer. But you can do analytic continuation in the dimension in that formula. So that means, and of course you expect that Feynman integrals have infrared or UV divergences, that its expression actually has divergences. You can just treat D in analytic continuation and you do a Laurent expansion near the critical dimension when you want to compute. So essentially everything I'm going to say is after having extracted the coefficient of the Laurent expansion, I'm working with finite quantities. And when I will discuss some class of graphs, actually I will select graphs that are just finite, so I don't have to do this expansion, but you can do this expansion as well. Okay. So the graph polynomial is actually the thing that completely characterizes your Feynman graphs, is an homogeneous polynomial of degree L plus 1 in Pn minus 1 that has a very, very, very special form. So this F is a sum over the internal mass parameters times the projective variables that are conjugated to the edges. So, and this is going to play an important role when I construct the geometry behind the Feynman graphs. Then there's the U polynomial, which is actually the homogeneous of degree L of monomials where the coefficients are 0 and 1. So for those, if you come from string theory, if you like to think that the Feynman graphs comes by degenerating a string, a Riemann surfaces with mark point, this is exactly the determinant of the period matrix of the degenerated Feynman Riemann surface. And V is a part that contains the kinematical variables. So what I want to point to you is that all the physical parameters, the internal masses, or the kinematical parameters of the external particles, they all come linearly. So if you think in a toric setting, as I will do in a minute, so in a sense, I mean, it's some restriction of a toric polynomial, but everything is linear in all the physical parameters. So once you have this graph, you can go back to, so if you have a graph, you can construct, of course, this F gamma. It's in every quantum field theory books. But if you have F gamma, then you can reconstruct the graph as well, because you know the number of edges is n, the number of loop is the degree minus 1, the number of vertices by Euler characteristic because it's a planar graph, is given by this, and then by looking at the coefficient here, you can reconstruct the incidence matrix and everything. Okay. So the thing is that now this Feynman integral is now this integral over this ratio of this, of these graph polynomials, right? Yes. Over the positive quadrant. And so actually you want to think that this is, the integrand is an algebraic differential form in the complement of the graph hypersurface. Okay. So first I want to say that all the singularities of the Feynman integrals are located on the graph hypersurface Yeah. But in general, the graph hypersurface are non-isolated singularities. So that, in a sense, is a complication when you want to understand what's going on. So the other thing that happens is that the graph hypersurface intersects the positive quadrant are exactly this point. So in a sense, that forces you to look at the relative cohomology. And so in a sense, for example, if in the case of a two-loop graph, which I will discuss that I discussed actually in some previous string math that is based on some analysis I did with Spencer Block. But so the elliptic curve will go through, this point here, and essentially what you would have to do is that you will have to do the blow up. And what you see is going on is that what we'll see later is that actually the internal mass is actually realizes exactly what you need for doing the blow up. So the message from these slides is that actually your Feynman integrals is a period in that motif. So once you have done the blow up and went to the relative cohomology. So as a consequence of that, okay, so now what's happening is that you are interested by the way the Feynman integral varies when you vary the physical parameters. So when you vary the physical parameters, you have a variation of Hodge structures, and by looking at the way this Hodge structure varies, then you understand that actually the Feynman integrals will satisfy a differential operator. So I'm calling this the Picard-Fuchs operator. I think of it as being the minimal order that acts on my Feynman integrals, but in general, it's inhomogeneous. So there's an inhomogeneous Picard-Fuchs operator that is satisfied by the Feynman integrals, and it's a big problem for physicists to obtain that differential equations, and there are many methods, and most of them are based on what is called integration by part identities. But it's very it uses a lot. If the graph turns to be a little complicated, it takes a lot of computer time, and it's very difficult to get. So in particular, even when you get something that is based on an elliptic curve, you tend to get you can from this reconstruct something like a Gauss-Manin connection that is too high. So then you have to reduce. So it's even difficult to see really what is the minimal order. Yeah. Okay. So let me think a bit torically. So there is one particular integral that is very similar to the one I have. This is the. So I want you to remember that actually the Feynman integral is integrating this differential form on the positive quadrant. Okay. But suppose you look at the one that is integrated on a torus, so which is actually associated with what you call maximal cut. Unitarity gives you. So this is one specific integral that I'm getting from the Feynman graphs. That is. So what's happening is that, of course, this period is a period of the Calabi-Yau hypersurface. That is, so if you, in a sense that if you take if you construct, you look at the Newton polytope. So look at, for example, the toric polynomial. That is actually the one that has all the same monomials as your Zeeman-Zig polynomial that you have in quantum field theory, but you don't impose the relations between the various coefficients. So that means you will have much more toric parameter here that you have actually in a physical in your physical Zeeman-Zig polynomial. So, as I already said before, the restriction to the physical locus is by the linear map. But by general, it's known actually that this period integral that I'm writing here is actually a period for the Calabi-Yau hypersurface that you construct in this toric variety, and actually it is obtained by a restriction of a very specific GZK A hypergeometric series. So you can take the generic from the Newton polytope. You generate the A hypergeometric series, and then you specify. You can even get the differential equation. Then you specify the specific values for the physical parameters, and then you get this guy on the nose. No, it satisfies the homogeneous one. Oh, I'm sorry, so I didn't say, yes. This one, because it's a period, is going to satisfy the homogeneous Picard-Fuchs, okay? So the homogeneous has to do with the fact that you have relative cohomology. So it essentially has to do with the boundaries of the. So here the point is that this. Oh, sorry. Oops. This is a cycle, right? So if the Picard-Fuchs acts on it, in cohomology, this is going to give me an exact form. So and this is just a cycle. So then it dies. But for the generic Feynman integrals, this is not a cycle, by what I said previously. So you will pick the boundary component, okay? So this is the way it works. So by this, you can think that, okay, you can derive the Picard-Fuchs operator, except that it's very difficult to restrict the D model that you get from the GZK system. So the only way I know how to do it these days is to get the A hypergeometric series specified to the physical locus. So you have to be careful because the system is resonant, but that's, I mean, it's well known how to do it. I mean, actually, it's in the case that I've looked at, so there is no issue to do it. And then from that, obtain the Picard-Fuchs operator. It's not very economical, but at least it's a way. So now let me see what we have actually, what we know so far about what are generic statements about motifs controlling Feynman integrals. So at one loop, we have hypersurface of degree 2 because the degree is loop plus 1 in Pn minus 1. So actually the motive is the structure of the one of D logarithm. So this is why actually it was mentioned in the talk by Fernando Alday that actually when you compute one loop amplitude you get D logarithm. So this is a well-known fact that physicists can understand, but as well you can understand it from motivically. So at two loop you get the graph hypersurface is degree 3 in Pn minus 1. So when n equals 3, so you get a degree 3 in P2, and then, so this is the starting point of our collaboration with Spencer Bloch. We show that actually it gives the motif on elliptic D-log, and then it matches exactly the construction actually of Braun and Levin of elliptic polylogs. So, but you see, when n is increasing, so that means when you have more external legs, keeping the loop order, then you are going, for example, to get a cubic in P3, in P4, etc. So then it's not clear exactly what is really controlling the geometry of the Feynman graphs. So what we think is that we have a conjecture that actually there is a motivic elliptic curve that controls the Hoche structures. And for example, for the cubic threefold, I mean, it's easy to show how the elliptic curve comes because this is just an application of the Griffiths-Clements for the intermediate Jacobian. But in general case, okay, so we have confidence that this is true, but we need to make sure that our construction works to all order. But so this is the idea behind that. So generally, at any loop order, what is really controlling the Hoche structure? So for a very specific family of graphs that are called sunset graph, when the loop order is actually correlated, so it's a n-1 loop hypersurface. So it's a n-1 loop graph. So that means the degree of the hypersurface is degree n in Pn-1. What I will explain in this talk and give a lot of gory details about that is that so you get a Calabi-Yau n-2 fold. And this is what the result of the construction with Chuck and Andre. So this is, for example, this graph where the sunsets are this. So this is the graph when you have one particle that comes in, one particle that goes out. So here it's a 1, 2, 3 loop. So of course it starts 1 loop, 2 loop, 3 loop, and etc. n loops. So it's a nice family of graphs because the graph structure is very simple. But as well as I said, I mean this thing comes actually in very physical quantities as TT bar production. So let me tell you what is the graph polynomial for this family of n-1 loop sunset. So the graph polynomial has this very nice Laurent polynomial form. It's because the kinematics is very simple. So there is here. So the internal edge mass is this. So this is just this factor. Then there is the reciprocal of the variables, and then so this is this Laurent polynomial minus p squared times, so that means when you multiply everything back together, you see it has degree, homogeneous degree n. So, and if you look at this graph in space-time, in two space-time dimension, because I want to look at the case when the mass are non-zero, so then the integral is finite. No UV, no infrared divergences. So you want to compute these Feynman integrals, which is this p square minus this Laurent polynomial over the positive quadrant. And here's the classical period where you have the same integral, but I just change the cycle, okay? So some of the people who are familiar with this Fano classification by the imperial group will maybe start to be seeing something that they may have seen, although what in the Fano search program, they tend to look at the case where there's no parameters. I mean, because it's a classification program, so they have ones or at most maybe some integer parameter. But yeah, I want these AMs to be real complex, whatever. But there's something very nice. For example, if you, for example, look at the special values of that integral, where everything is 1, okay? You could show that actually this period, that as I told you, the Feynman integral is a relative period, is actually a pure period, because the symmetries, by the symmetries of that, you can apply it and see that actually you can rewrite it in terms of an integration over a cycle that has no boundary. And the thing is that why do you want to look at this? Well, you want to look at this because these specific values, this is a number. So Broders for many years, I mean, and he's still doing it, but started many years ago, doing numerics and identify that this value of the Feynman integrals is given by L-value functions evaluated in the critical band. And these L-value functions are from 9 loops, if I remember well, are expressed from moments of Klosterman sums over finite fields. So essentially, I'm not going to prove this Broders relation to all order, but I will tell you how we proved, I mean, the relation between this period and L function values for the case that we know. So for example, for n equal 3, you have an elliptic curve. So the graph hypersurface defines an elliptic curve. And so the value of the Feynman integral is just zeta 2 times 1/2. But that's easy. Essentially, this is just, you see it because it's an elliptic curve. For n equal 4, the graph hypersurface defines a K3 that I will describe in more detail later. It's a special K3 surface that has pK rank 19, and the value of the of the Feynman integrals is this L function, LK3 with this square root of 15, whatever, and evaluated at 2. And actually, what we just prove is that since you know this guy is a period, essentially you want to prove a special case of the Lin conjecture relating period integrals to L values in the critical band. So, and this is what we did. So you have the L value that is the L function associated with the cohomology of the K3 surface. Then the modular form here that you have to plug in is this weight-free modular form. Yeah. So you have the 15 is there, and then the divisors and this theta function. And of course, so this guy satisfies this functional equation. I mean, it is weight-free. So S to 3 minus S. And again, and you see 2 being smaller than 3, this is really in the critical band. Okay, so here we could prove it in a sense because the structure is that there's complex multiplication, so it's easier to prove. But it's a case where actually not only the Feynman integrals give you incarnation of this Lin conjecture, and in a sense, which is, I think, a very, very nice way to approach these very deep conjectures, and as well, by looking at the in specifics of this Feynman integral, you can even prove it. The other thing that is very nice with this family of sunset integrals is that if you convert from, if you use a direct space representation, so you are not in momentum space and direct space, the propagator in 2 dimensions is a Bessel function. So the Feynman integral is product of Bessel function. So it's a 1-dimensional integral of product of K0 and I0 Bessel functions, okay? So the difference between these 2 K A0 and A0 Bessel functions is that this is the same integrand, but here integrate between 0 and infinity and integrate between the circle, okay? So my classical period, so this is a period of, this is a relative period, this is a pure period, and you see the difference between the two. Here in that case, it's not the way you integrate, it's just the swap between the I0 and the K0. And actually, this is a very, very nice, again, incarnation of what Javier Fresan and Josan have constructed recently in terms of what is called exponential motives. It's a very, very, important application. You can use their setup to understand these relations. Okay, so let me now describe my sunset. So my sunset graph polynomial is this. So in general, if you have a graph polynomial for a Feynman graph, you will have much more kinematics. So the symmetries I'm going to use here, are going to be lost. But at least for this family, they are there. So you realize that actually this sunset graph polynomial is a character of the adjoint representation of the AN. So this is the linking diagram of AN, or AN minus 1. So then you realize as well that the Newton polytope for the sunset graph is reflexive and has only the origin as interior point. And actually the origin is parameterized by p square. So p square is a very distinguished parameter in my construction. And so you can construct a toric variety as the Cremona graph of the transformations that is the inversion. So that means your toric variety is obtained by blowing up exactly what I told you at the beginning, so the blow up of this point. And actually the parameter that enters the blow up are exactly the mass parameters. So this is a message that essentially is very important for the studies of Feynman integrals in that context, if you want to think torically about any Feynman integral, is that internal masses are associated with the blow-up you need to do torically. So a lot of people have, in physics, studied a case where the masses are 0. So when the masses are 0, I'm losing this. So the thing is that it's become more singular. So in a sense, in a way, because there are even more singularities, for some reason the integral is a simpler object to study from physics point of view. But from my point of view, it's not so nice. So I prefer to keep internal masses. So for example, let me look at the two-loop case. So the two-loop case, this is the internal max, this is the U polynomial, and this is p square, okay? So what's happening is that what I told you, my elliptic curve goes through these 3 points that are, the intersection of my coordinate system, projective space, so I have to do my blow up, and it's precisely what this thing is doing, okay? So then I'm getting this hexagon. But so that means my toric variety is exactly dp6, because it's the p2 blown out at 3 points. So what's happening is that if you look at it, so this is from the root lattice of A2, you see that actually this is my hexagon. And what you see is that actually the masses here are exactly giving you an F partition that is here in gray. So what I'm telling you is true to all n. So the description I'm giving to you is that this is always true, is that the mass parameter that I'm having to the all orders of this sunset family is going to parameterize these Neff partitions. And this is telling me how special is this family inside my, in the toric, as a toric restriction. So when p square varies, I can define a pencil. So this is my pencil, okay. So the fiber at infinity is the normal crossing divisor, and by generic argument, the normal crossing divisor actually, because it's proportional to the is equivalent to anti-canonical divisor, then you are getting Calabi-Yau n minus 2-fold, okay. So this is the way you are getting a Calabi-Yau n minus 2-fold. Yeah. So, of course, the problem is that when I'm starting to have some more complicated, so what's going to happen when I'm going to have some at the same loop order, but some more external point, I'm going to mess up the part that is here in my Simonzik polynomial. So some of these things are not going to work that easily, but still, okay. So we hope something is going to survive. So if I look at this graph here, I see that it's, so this is, I can see that it's a big one loop with another loop in it, okay? So in a sense, I mean, if I go to any loop order, I see that there are naturally a natural inclusion, I mean, that you just see by drawing the graph, by looking this way. So that means if I draw an horizontal line, it's like the matryoshki, so where you have the one loop, the two loop, and then etc. So it's like there's this nice iterative structure. So actually, the iterative structure is pretty. I mean, it's obvious if you then switch from this presentation of so my family is defined by the vanishing locus, I mean the graph hypersurface of the Simonzik polynomial. Actually, it's a simple exercise to show that it's completely equivalent to this complete intersection. Okay, so essentially you just move this guy to the other, and then you introduce an extra variables, or if you solve for x0, then you get this, right? Okay. So now, once you have done this, then this. Oops, I'm sorry. This iterative structure is totally obvious because it's just a substitution. Here I relabel what I call this to this. And actually this is giving me the way I will think about an elliptic, my Fiberation. And then by using this construction, then you really see immediately that xn minus 1, so there's this Fiberation. So xn minus 1 is fibered. I mean, the fiber is xn minus 2. So there is this Fiberation of graph on one to the other. So what is the consequence? So the consequence as work is that then we have a family of Calabi-Yau n minus 1 fold, which is going to be actually obtained by the previous one from the n minus 2 fold. So that means the level of the Feynman integrals, there is this nice iterated integral representation. So the Feynman integral is obtained by the Feynman integral at the previous loop order, and then this is the Fiberation. T is my Fiberation parameter. Or if you I'm sorry, there's two T's. I'm sorry, this should be P square, this one. So I'm integrating over T. Yes, this is a function of P square, so this is P square. So, and this is the Fiberation parameter, and this works for the period. So actually, for example, this allows you to crank up. So if you know the Picard-Fuchs operator as some order, then you can crank it up and get it to the next order. So let me discuss a little bit the geometry of the two-loop one. So the two-loop graph is this. So the pencil, so this is a pencil of elliptic curves, because this is an elliptic curve. When P square varies, I'm getting a pencil of elliptic curves. So when I have generic values for the internal masses, then I have this. I always have an I2 fibers at P square equals 0, an I6 at P square equals infinity, and then I have 4 I1 fibers at what is called the threshold, the pseudo threshold. So there are only, because it's a square, there are only 4 independent variables. So when all the mass are the same and non-zero, so what I'm getting, the I2 fiber stays, the I6 stays, but then the 4I1, so there are collisions of fibers, and I'm getting 1 I3 and 1 I9, okay? So actually this one is very nice because it's in the Beauville classification, and it's a modular curve, x16. And so what we showed with Spencer is that actually the Feynman so the motive is just equivalent to this, which is, once you see it, I mean, it's exactly the motif on an elliptic D-log. So that's easy. That was the easy one. So now, by the iterative construction, I can look at the next guy. So the next guy is defines a pencil of K-free surfaces. So what I want to say is that if you look at the generic, so if you relax, so here there's a very special relation between the coefficient in the Laurent polynomial, okay? If you relax, so I'm going back to the remark at the beginning of the talk, if you relax these specific relations, you keep the same monomials, but you put, I forgot, 11 different monomials, then you get a K-free hypersurface, but it has Picard rank 11. So this is what I'm saying about the difficulty to start from the GZK construction and understand actually the specifics of your family, because if you are, theoretically you see only Picard rank 11, but actually you are Picard rank 16. So when you do the specification to your physical locus, then the restriction, something happens to your system, and then the Picard rank changes, okay? So we understand it completely because we see how to construct the transcendental lattice in general and then go to this case, but this family is simple. So that means for general Feynman graphs, I mean, it can be very tricky. But this elliptic fibration, I mean, so actually by the iterative construction I described to you, so anyway, so what you can do is that you can then construct understand what is actually this pencil. So you see when the four masses are different, you have this type of fibers, the Picard rank is 16, and so you're 17, 18, 19, so this is the cases. So here, in this table, I've been using this Fiberation construction, and for example, when I go from what I was calling two loop to three loop, so you see M4, so one of the new mass that appears comes into my Fiberation construction. So this is what I call M4 here. So you see, depending on how your parameters here are identified respect to the guy that is involved into the fibrations, you see that even the model veil is jumping. So yes, so you see there's some interesting jump in the model veil rank. So in a sense, we have a total control of everything you want to know about these K-free surfaces. And so the case with the peak 19 was already considered in a previous work with Spencer and Matt, where we show that actually this is a motif on an elliptic free log, which is given by this. So this is the complete, the normal crossing divisor. And so that we are happy. And it turned out actually the Feynman integral is this, we could express completely the Feynman integral using elliptic free log. But clearly in these cases, this is no longer true. So this is why you need to understand, I mean, if you try to guess what's going to happen in a generic mass case from what you know from the all equal mass case, I mean, it's a very naive approach. So from this construction, I told you I can construct the Picard-Fuchs operator. And just to give you a flavor of how complicated this is, so of course, if I use the GZK construction, I will get my system of differential operator, the GZK differentials, okay? Immediately. I put the graph polynomial, I do it with Sage, I push one button, and I'm getting it. Then the point is that I want then to reduce this thing on my physical locus and extract the minimal Picard-Fuchs operator, my ODE. And for those who have already played with this GZK construction, I mean, you can see it's very, very difficult because you see the generic, the Picard-Fuchs operator for the rank 16 case is order 3 or order 6, of course, because peak is 16. But the coefficient that multiplies this operator is a polynomial in my p-square variables, but is of degree 25. So there's one piece of that guy that is indeed the location of all my bad fibers. So all these guys they are the fibers associated in physics term to the position. So there is of the thresholds. So I know that there is going to be some regular singular point at the position of the bad fibers, but there is a piece in that polynomial that of degree 17 that has only apparent singularities. So already, if you are, I'm not yet talking about the inhomogeneous term, right? But already just at the level of the pure period, the classical period or fundamental period, if you want to call it, and then you already get a beast that is quite. I mean, this is why it's so difficult to compute explicitly when you do it. But what is very nice here is that actually we can follow, once we have this construction, what happens when you start specifying the internal parameters, and you really see that then you get from an order 6 Picard-Fuchs operator to an order 5 by factorizing an order 1. And then there are two ways to go to again then specify the internal parameters, which give you, in both cases, there are two different order 4 operators that are obtained by factorizing an order 1, and then you get at the end to the same order 3 Picard-Fuchs operator that we had constructed before. So this is really something that is very, very pretty complicated things to do, and I don't know any way to a priori predict the order of the Picard-Fuchs operator in general, or by just looking at the graph. And if I am torical, I'm just off. So in a sense, it's so this is why for this family we got to do it. So let's go to the next case. So we have a pencil of Calabi-Yau threefold, but then we have a pencil of nodal Calabi-Yau threefold. So I'm just here writing just the case for one of the H12 or H equal H21, actually, for any resolution, for a small or big resolution. So you have 30 nodes. This is when all the masses are different. H1 is 5. When you go to the one mass, so all these guys are the same, but p square is different from that, then you get H1 is 1, and you had 35 nodes, so you get 5 more nodes. Okay. But that you can construct it. And what happens is that when all the parameters are the same, which is the case of the period I mentioned it, then you get 0, and then you get something that is the birational to the Bartnietto quantic. So then it happens the following, that the Feynman integrals, as Broders discovered by numerical experiment, is 48 zeta 2 times the L function, this L function evaluated at s equal 2, where the modular form that comes in is a weight for level 6 modular form, okay? This is this, and there's a square, okay? So first, when you look at it, he really did it by numerical experimentation. When you look at it, then you realize that this guy is precisely a square of a eta product where you have all the divisor of 6, 3, 2, 1, okay? I told you that the case of the two-loop sunset, when all the parameters is 1, I'm getting a modular curve that is x16. So then you really see that, okay, then there must be a relation to this x16 modular curves. And if you think that actually here you have the number of masses here, is such, then when you look at the elliptic Fiberation, then you realize that indeed this quantity here is birational to a product of two of these sunset two-loop, which is this elliptic curve case. So that makes so then you realize that actually, then you understand how this geometrical construction I've been describing naturally motivates the appearance of this modular form that is just the square of the eta product that is naturally associated with x16. So, but what you can do is that you can compute the L function from the cohomology, from the middle cohomology, H3 of Q, and Elena Veril did it. And indeed, I mean, she found that actually then the L function is precisely the L function associated with that modular form. By weight, it has this functional equation. And then what you have is that then, of course, 2 being smaller than 4, then again, we have the Linz conjecture, an incarnation of the Linz conjecture. And to that you can prove, I mean, this is pretty amazing. So what I'm saying is that no, I mean, I haven't done it, but I'm pretty sure somebody more mathematically advanced than me, or maybe me, if I learn enough mathematics, can prove all these, the Broders relations. Okay? So now let me talk about mirror symmetry. So this free loop sunset integrals that was evaluated on an elliptic D-log with Spencer, the elliptic D-log is on the Hodge side, so the B model side, if you want to use a mirror symmetry language. If you go to the A model side, you can do a brute force computation. So you can rewrite your Feynman integrals as this classical period, which is defined from the Laurent polynomial, times this. So R0 is this logarithmic Müller measure. I mean, the derivative of this respect to P square is this. And then this formula, I like it because you see, you make explicit all the mass parameters. So in that language, what's happening is that you have this sum where all the parameters in this series expansion is actually the mass parameter dressed by this Q, big Q, that is the exponential of R0, and they are actually the Kähler parameters. So essentially, the mirror map that goes from the elliptic D-log, I did not write the elliptic D-log explicitly in front of you, but the elliptic D-log was a function of Q, which is expressed in terms of the complex structure of the sunset elliptic curve. Here you have a big Q, which is defined from the exponential of that, and the mirror map is precisely switching between the complex structure of this elliptic curve to the scalar parameters. But that you can just, I mean, if you know nothing, you can just do it by hand, you compute, and then you get this. Then you extract these numbers. And then what you find is, so what are these numbers? So these numbers actually, so I have an elliptic curve at 2 loop. I can define my Yukawa coupling this way, which is this derivative. So this is, I repeat, this is my algebraic form that is defined as a Poincaré residue from my graph polynomial. I define my natural Yukawa coupling from this for the elliptic curve. Okay? And then what happens is that then you realize that actually if you embed my DP6 that I described before into a non-compact Calabi-Yau threefold by adding this plus UV equals 0, that means you are constructing this Ori-Vafa threefold, it's non-compact, then actually the Yukawa coupling of the non-compact Ori-Vafa threefold descends, I mean the local Yukawa coupling, I mean so it descends to precisely the Yukawa coupling I have on my elliptic curve divided by the cube of my classical period, the cube because it's the cube here. And then by the fact that it comes this way, you have these relations that tells you that actually the numbers that are here in my Feynman integrals are exactly the local Gromov-Witten invariant that you can extract for this Yukawa coupling construction. Okay? So that was the remark we had. I mean, we proved this, but I mean, this is the construction we had. And then actually these numbers, the local Gromov-Witten invariant, as we showed, they are related to the BPS counting of curves through this covering formula. Everything fits perfectly. And I'm telling you, this is a graph that is a quantum field theory graph. There is no string theory there. There is no and actually, as you can see, actually it agrees as well. So this number agrees with the BPS invariant computed by Albrecht and collaborators. Okay, so you could say this is fine. Well, except that there is one big problem with, I mean, one big technical problem is that in the paper with Matt and Spencer, what we did is that we took a compact Calabi-Yau threefold that we degenerated to this to this Ori-Vafa model to do the computation. So it's very, it's very difficult to implement. So in a sense, if I want to do the next case, where I will have, when I will have, the K3 case or the higher order, I will have to compute all this local Gromov-Witten invariant through this construction. And honestly, I don't know. I would be very happy to convince Albrecht or his collaborators to do it for me, but honestly, this is difficult. So one of the things that I'm not very, you realize is not very satisfying is that the mirror map here actually puts all the parameters at the same level. All the masses and the p-square are all treated in the same way. But the p-square was the center of my polytope, and p-square as well is the thing for my pencil. So p-square is special. And so actually what we realize is that actually this local Gromov-Witten invariant are actually equal up to some factors to the relative Gromov-Witten invariant for the case of the sunset. I added the del Pezzo 6, dp6 relative to some divisor, okay? And the divisor are the ones that are selected by my mass configurations. So that means I can now recast this mirror symmetry statement in a statement about a mirror symmetry between a Fano variety and Landau-Ginzburg symmetry using that will involve actually the computation of this relative Gromov-Witten invariant. So just, since this is the end of the talk, but let me tell you what is the Landau-Ginzburg. So in that case, the Landau-Ginzburg superpotential is exactly the graph polynomial. W is f of this, but it's an homogeneous degree n polynomial in Pn minus 1. So it's a very simple exercise to compute the central charge, which is 3n minus 2. And indeed, it confirms the fact that I explained before, that actually I have a Calabi-Yau, this graph, the geometry of this graph is defined by a Calabi-Yau n minus 2-fold. So now what's happening is that what I call the classical period here, which is defined which is actually the thing that physicists compute, which is the maximal cut, by the Fano-Landau-Ginzburg mirror symmetry statement, should be identified with the regularized quantum period of the Fano. And this is precisely what we are doing. And but then to compute the relative Gromov-Witten invariant, we have to use some technique developed by Tseng and Yu. Actually, Yu is a postdoc of Chuck Doran. And the advantage of this computation is that now the relative Gromov-Witten invariant are much more easy to compute. So this is precisely the recasting of the new way to see what are Feynman integrals. So Feynman integrals are actually, at least for the sunset, a realization. They are this period integral that are actually they realize actually the mirror symmetry between Fano and Landau-Ginzburg model when the Landau-Ginzburg model is associated with the graph polynomial. The genus zero Gromov-Witten invariant that we found with Spencer and Matt in this graph actually now it can be proven to all order that they appear through this relation between local Gromov-Witten invariant and relative Gromov-Witten invariant once we have recasted the whole problem in that context. And so what's going to happen for a generic Feynman graph? So I say for a generic Feynman graph, the Calabi-Yau construction is lost. So one idea is maybe to look at multiple potential Landau-Ginzburg model, but although this thing is pretty well understood, this thing I have less understanding of the way it works, although physically you want to associate a potential for all kinematical variables. That seems to be a good idea. But at least for the two-loop case, which we are looking with Spencer and Matt, the DHT construction for Turing degeneration that Chuck described in string math in Sanya seems to apply directly. And that seems, at least for the two-loop case, a way to completely crack the problem of what are these Feynman integrals. Thank you very much.
Question?
an alternative formulation of the question. Beyond suggesting which motives to consider, is there any input from the quantum field theory in the rest of this discussion, or do you just do algebraic geometry once you...
I do just algebraic geometry, yes. So the point is that this is a discussion I had with some of my colleagues in Paris, whether or not we are learning something new in math, okay? And so far I've been applying things that are known in algebraic geometry and motifs. I mean, it's difficult to implement, but I mean, you can do it, right? But I'm expecting that maybe we will get something, if you start looking at graphs that are of some higher loops and things like that, you would certainly have to learn something interestingly new in motifs. So, but I don't know so far, okay. But this relation with these exponential motifs of Ressan and Jossen is very fascinating. So, and this is already one place where you see some new motifs appearing.
Linkages, yeah.
Yes. Where we were.
I think it's just the same variety. This is your three Calabi-Yauch, very special one. It's hexagon with all sides equal 1 on the plane after rotations.
Okay, so thank you. Yeah, so just to okay. So just to test. So when coming here, Maxime was telling me about some specific Calabi-Yau, and then apparently it's the same. So okay, thank you.
If no other questions, thank the speaker again.